I was 21 when I first discovered simulation. I saw these beautiful, colorful, complicated models, and I remember thinking, this is too advanced for me. I honestly thought, maybe I can touch this field after 10 or 15 years of experience. I didn't think a student like me could even begin. But curiosity won. I opened the software and built a simple beam, ran the simulation, and the stresses didn't match the simple equation or the calculations I did on paper. I thought the software was wrong. So I went to my professor in college and asked him why the results in the program was different from my calculations. That stupid question was the beginning of everything. 3 years later, I've published research, I've completed real engineering projects, and I realized something important. This field is not for geniuses, it's for people willing to understand it step by step. So let me show you how to begin. I told you that I started my journey by opening the software, but honestly, that was my first mistake. When something went wrong in my simulation and the results didn't make sense, I couldn't explain it because I didn't understand the mathematics behind it. And that's the truth most beginners don't realize. Simulation is not about the colorful diagrams you see on the screen. Those are just the interface. Behind every beautiful stress plot or velocity field, there's a large, ugly matrix that the computer is trying to build and solve. That's what really is happening. So if I want to make the journey clear for you, we have to divide the simulation journey into 2 parts. The first part is the mathematical foundation, like understanding the governing equation, the discretization method, and the solver you will use to solve the matrix. The second part is the software, where you build the geometry, apply the boundary condition, and visualize the results. But the visuals only make sense when you understand the mathematics underneath. Let's start with the mathematical foundation. If you want to build a mathematical model, before you open any software, you need to understand one thing. What physical phenomena are you trying to model? Every simulation starts there. If you want to model fluid flow, the governing equation or the Navier-Stokes equation. If you want to model electromagnetism, you start from Maxwell's equation. If you want to model solid mechanics, you begin with the equations of elasticity, linear or nonlinear, depending on the situation. Everything began with a partial differential equation that describes how the physical quantity evolves in space and time. Let's take a simple example. Imagine we have a string, and we oscillate it from one end and the other end is fixed. We want to study the shape of the oscillation that's happening, the amplitude, maybe the frequency. If we search for the governing equation for this phenomenon, we find the wave equation. It's one of the most famous partial differential equations. In one dimension, it has a beautiful general solution. It's a sine wave, and that makes perfect sense physically. A string oscillates in a sinusoidal manner, so the mathematical solution is sinusoidal. Inside the solution, you see the amplitude, the frequency of the oscillation with time and space. Everything has physical meaning. But now let's move to real engineering. Suppose instead of a simple 1D string, we have a complex 3D structure like this pen or this cup or any other complicated one. Say now I flick it. We want to understand how a wave of stress travels through it. Now the governing equation becomes too complex. The geometry is irregular, especially it's 3D now. You turn to the equation and it's now not simple. There is variables like x, y, and z, and t. The variables are irregular. It's not a straight path. Like the string, it would be impossible to have a solution. So engineers were like, screw this. So what do we do now? Engineers thought we may divide the domain into many small elements or cells. On each small part, we assume a similar local approximation of the solution. Then we assemble all of those local approximations together to create a big ugly matrix, as we talked about in the previous video. That matrix is what the computer is actually solving, which consists of thousands or maybe millions of numbers and equations. There are many ways to perform this partitioning. The most popular one in engineering is the finite element method, but it's not the only one. There is the finite volume method, the finite difference method. There are also meshless methods, spectral methods, and even approaches like lattice-Boltzmann. There are analytical element methods. There is also an infinite element method. All of them are different strategies for applying the PDE into a complex structure in an approximated way, of course. And now comes the final step of the mathematical side. We have a matrix, we need to solve it. There are different ways to solve it, like Gaussian elimination, LU decomposition, iterative solvers, there are segregate solvers, and each choice affects speed, stability, and accuracy. We'll talk about that later in another video. So the mathematical part of simulation has 3 layers. First, what is the physical phenomena we're trying to solve? Second, what numerical method are we applying? Finite element, finite volume, etc. And third, what solver will you use to solve the assembled matrix? That is the real foundation of simulation. Now that you understand the numerical model behind the scenes, you now open the software and start applying your knowledge. There are many options out there. There is ANSYS, Abacus, and my personal favorite, Comsol Multiphysics. We're going to hover over it a little bit just to show you how simulation is done. Comsol is what we call a multiphysics software. That means you're not limited to just one phenomena. You can couple fluid with structure, electromagnetism with heat transfer, everything interacting together. Let's take an example we talked about, wave propagation. Suppose I want to model a wave traveling inside a 2D fluid domain. First, I define a geometry. Maybe it's something simple, a rectangle. Then I choose a physics interface. That's a fluid flow. Now I apply a boundary condition, which is like the exciting force for the domain. Maybe I prescribe a sinusoidal excitation at the boundary. That sine wave has a frequency and it has an amplitude and a phase. Then I will partition the structure, or what we call creating a mesh. And since fluid problems often require accuracy, I will refine it. We're going to talk about meshing in another video. It deserves its own space. I want to see in time, so I'm going to create a time-dependent study. After that, I choose a solver, and there are multiple choices. And then I hit run, the simulation starts. And now, when you see the wave propagating inside the domain, when you see the velocity field evolving, and the pressure distribution changes, you don't just see colors, you see mathematics coming alive. So this is kind of my journey of simulation. Simulation is not magic, it's structured thinking. If you want to go deeper into what simulation really is and how it can save lives, I made another video explaining that. You can find it here. In the next video, we'll break down subjects like meshing and solvers and numerical stability. If you want, you can subscribe, and I would appreciate your comments and ideas in the comment section. Thank you for watching.